Okay, this is the experimental setup for the lab, where we are going to be using the data measured when we operate a light-emitting diode in order to determine the value of Planck's constant. So we have a number of things that we're looking at here. On the right-hand side of your view is a power supply, and then we have two meters. One is a blue-colored meter, and that's the voltmeter. That's going to be what I'm going to use to measure the potential difference supplied to the LED. We also have an ammeter, which is the red meter, and that's the meter that you are going to have to be reading to measure the current through the LED. And when the time comes, I will zoom in so that you can see that scale a lot better than you can see it right now. In between the two meters is an LED that's connected to everything. The LED isn't lit right now because the power supply is off. You certainly don't need to worry about how everything is wired here. It's kind of a confusing jumble of wires, but the bottom line is when I turn the power on, if the LED lights, we're going to see a potential difference and we're going to see a current. With that being said, if I turn the power supply on right now, you can see that the meter on the left, which is the voltmeter, is registering a voltage. It's approximately 1.4 volts right now, but the meter on the right, which is the ammeter, is not measuring a current. And if you look at the LED is not lit. That's because LEDs only operate within a small range of applied potential differences. And this LED won't light until we get to around probably about 1.8 volts. The data that we're going to be collecting in your data table is going to be ranging from voltages of 2.2 volts all the way up to 2.8 volts. So first of all, let's get the LED lit up before we collect any data. I'm going to increase the voltage by turning the dial on the power supply, and you can keep an eye on three things if at all possible. Keep an eye on the voltmeter, which is going to be showing that the voltage I supply to the LED goes up. Keep an eye on the LED and the ammeter. The ammeter will not show a current until the LED starts lighting. So at this point, the LED is lit. It's not that bright. And I have a feeling that on the video, the color of the LED is probably going to be a white color. It's probably going to be washed out. But the LED is a red LED. If you look very closely at the ammeter, it is showing a very, very small current. If I continue to increase the voltage, then the current goes up, the voltage goes up, and the LED gets brighter. So now we're going to collect our data. The first thing that you need to know, and I did a little experiment with a diffraction grating and interference here to find this out, is that the LED is emitting light of a wavelength 7.6 multiplied by 10 to the negative 7 meters. So you're going to need to know the wavelength of the light. It's 760 nanometers. 7.6 times 10 to the negative 7 meters. Now what we're going to do is we're going to start collecting the data. I'm going to zoom in so that you can see the ammeter, and we'll talk briefly about the scale that you're looking at on the ammeter. We are set up to read the scale at the top of your screen. Specifically, we're looking at the numbers 0, 100, 200, 300, 400, and 500. So to give you an idea of how that scale operates, you can see from the video that that needle is somewhere between 20 milliamps and 30 milliamps. And if I had to estimate, I would probably say 22 milliamps or 23 milliamps. And part of your evaluation is going to be the numbers that you actually record. So that's how the scale works. Now what I'm going to do is I'm going to be increasing the voltage, starting with the minimum voltage in your data table, which is 2.2 volts. So I'm going to adjust the voltage to 2.2 volts to begin with. Right now, the voltage being supplied to the LED is at 2.2 volts, so you have to record the ammeter reading that corresponds with 2.2 volts. Now I'm going to increase the voltage to 2.3 volts. The voltage is currently at 2.3 volts, so again, corresponding to 2.3 volts, there's a current that you need to read and record in your data table. I'm going to go to 2.4 volts now. So right now there's 2.4 volts of potential difference being supplied to the LED. Again, you need to record the current that goes along with the 2.4 volts. I'm going to adjust it now to 2.5 volts. So it's sitting at 2.5 volts right now. Again, you want to record the current. I'm going to go to 2.6 volts. That's currently at 2.6 volts. Now I'm going to go to 2.7 volts. It's sitting right now at 2.7 volts, so you'll want to record the current. I'm pretty sure that when I set up the data table, it goes up to 2.8, so I'm going to go up to 2.8 volts. And now I've got 2.8 volts of potential difference being supplied to the LED. So hopefully you have all of your data recorded. Of course, if you want, you can go back and look at the video again and pause it wherever you need to. Remember that the wavelength of light being used is 7.6 multiplied by 10 to the negative 7 meters. Right now what I'm going to do is I'm going to go through a description of how you're going to perform the graphical analysis, as well as talk briefly about what I'm going to expect from you in the work that you submit. Okay, what I would like to do now is go through the graphical analysis and explain to you how you can use the graph of the data to determine the value of Planck's constant. First of all, when you plot your data, you're going to have 6 or 7 data points. I've only got 6 up here. I think you're probably going to have 7, but it doesn't matter. You're going to plot the data and then draw a line of best fit that represents the data. Remember that when you draw a line of best fit, you're not connecting the dots. You're taking a single straight edge like a ruler, putting it down and drawing a single line that you feel represents the data fairly. Notice that on the vertical axis, the numbers are in hundreds. So it goes from 0 to 100 to 200 to 300. But when you look at the units on the vertical axis, they are in 10 to the negative 3 amps. So what that means is you can plot the data using the milliamps that you measured on the meter, but when it comes time to using that data, we want to use standard units and include 10 to the negative 3 amps. So now how do the features of this graph allow you to determine Planck's constant? Well, before we go on, you need to understand something that's absolutely crucial to any graphical analysis. And that's that one of these variables is x, and one of these variables is y. So the current in this experiment is the responding variable. It's the y variable. The potential difference is the manipulated variable. And the reason that becomes important is when you do a graphical analysis, you want to compare the physical equation, which is what we're looking at now, to the mathematical equation. Now, since we get a straight line, the mathematical equation is y equals mx plus b. If we are going to compare this physical equation to the mathematical equation of y equals mx plus b, we have to rearrange this equation for y. And our y variable is the current. So my first step in rearranging this is to write QIR equals Q delta V, and I'm subtracting from both sides HC over lambda. Then I'm going to have to divide every term by QR. So I'm going to divide this term by QR. That will leave me with I on the left side. But if I divide that term by QR, I need to divide every term by QR. And for the third term, when I take HC over lambda over QR, what I'm going to do is write over QR over 1. And the reason why I'm doing that is because we have a rule in mathematics for how you divide one fraction by another fraction. You take the numerator fraction and multiply by the reciprocal of the denominator. This just makes it a little bit easier to understand what we're going to get for that third term. On the left-hand side, the Q cancels with the Q, the R cancels with the R, and we are left with current. On the right-hand side, in the first term, the two charges cancel, and we're left with potential difference over the resistance of the LED. Then we have minus HC over lambda, and we are dividing by QR over 1, so we have to multiply by the reciprocal, which is 1 over QR. In the next step, I'm simply going to pack all of those variables and quantities together in the last term to get current equals potential difference over the resistance of the LED minus HC over lambda QR. Now we want to compare that equation. This is the physical equation. We want to compare that to the mathematical equation. And since you get a straight line on the graph, the mathematical equation is y equals mx plus b. Now I've left a space between those two because it might not be obvious to you what everything is in terms of matching up from the physics equation to the math equation. I think it's pretty clear that I is your y and delta v is your x, but I would like to rewrite this physics equation just a little bit different. I'm going to write it as I equals 1 over r multiplied by delta v. Delta v over r is the same as 1 over r times delta v. Then minus hc over lambda q r. And now we can do a direct comparison. Our current is what's plotted on the vertical axis, which means our current is the y variable. On the horizontal axis, we have plotted the potential difference, which means our x variable is potential difference. Now, before I get to everything else, I would like to make one minor adjustment to how I wrote the equation. I have I equals 1 over r multiplied by potential difference, and then I have minus hc over lambda qr. I am going to change that minus hc over lambda qr to plus a negative. That way, both of the equations, the physical equation and the mathematical equation, have plus something at the end. So now we can finish our comparison. I apologize in advance for the bright color, but the slope is always the coefficient of the variable that's on the horizontal axis. And what that means is the slope of your graph will be 1 over the resistance. And don't forget, the purpose of this lab is for you to determine Planck's constant. Let me change something here to make this a little bit more visual. This is 1 over r, and this is the slope. Finally, the last thing that we can compare is that the constant added to the variable term in the equation matches up with negative hc over lambda qr. Okay, now h is what we're trying to determine, and h is contained within the y-intercept of the graph. Okay, so if you want to determine Planck's constant, we've just discovered that the y-intercept is connected to Planck's constant with this relationship. So in order for you to determine from this relationship that I've just written down Planck's constant, you need to know the value of every other quantity in that relationship. So do you know the speed of light? Well, I hope so. It's on your formula sheet, 3.00 times 10 to the 8 meters per second. Do you know the wavelength of the LED? Yes, you do, because I did a little experiment with a diffraction grating, and I told you what the results of that experiment were. The wavelength of the light was 7.6 times 10 to the negative 7 meters. Do you know the charge of an electron? Well, of course you do. It's 1.6 times 10 to the negative 19 coulombs. You also need to know the y-intercept, b. Do you know the y-intercept? Well, what you have to do is look at the graph and read the y-intercept. And by the way, if the y-intercept is negative 180, it's actually negative 0.180, because you have to include, in any measurement on the y-axis, you have to include this 10 to the negative 3. Regardless, you take a look at the graph and you know your y-intercept. Do you know r? This is the last piece of the puzzle. If you know r, then you can put in r, c, q, lambda, and the y-intercept and calculate Planck's constant. You don't know r. So how can we find r? That's our obstacle. Well, we can find r because the second thing that was revealed in our graphical analysis is that the slope is the reciprocal of r. That's highlighted in purple. The slope is the reciprocal of r. So do you know the slope? Well, you can find the slope. And I haven't had a chance to really talk to you too much about finding slopes on graphs because we've been doing this long distance. But when you find the slope of this line, it's important for you to pick a couple of points that are very far away from each other on the line. And it's also important that you do not pick data points. So if you pick a couple of points, you can draw a triangle on there, and that triangle can be used to determine the rise and the run. Don't forget that your rise is going to be found by looking at the numbers on the vertical axis, but you have to include 10 to the negative 3. Your run is going to be found by looking at the numbers on the horizontal axis. So your slope will have units of amps per volt, whatever that means. It doesn't matter. You can find your slope. So once you know your slope, you can calculate the resistance. And once you know the resistance, you can calculate Planck's constant. So in the end, everybody, you are going to be calculating this first, and then using that along with all of the other information that we've compiled, you're going to find Planck's constant second. Now expect this explanation as part of your assignment. You have to find a way somehow to communicate everything that I've talked about here, and especially to communicate how things in the mathematical equation compare to things in the physical equation. So if you just say in your assignment, well, the y-intercept is negative hc over lambda qr, and you don't explain where that comes from, or if you just say in your assignment that the reciprocal of the resistance is the slope of the line, but you don't address where it comes from, you're not going to do well on the assignment. You need this analysis. I think that covers everything. You go through this analysis that we're looking at right now so that you can conclude that the y-intercept is equal to negative hc over lambda qr. By the way, your y-intercept will be a negative number, so those negatives will cancel. As well, coming out of that analysis, you have the statement slope equals the reciprocal of the resistance. So you find the slope, you use it to determine the resistance, you find your y-intercept, and you use it along with your resistance, the speed of light, the wavelength, the charge of the electron, to determine Planck's constant. And if you do a really careful job of your measurements and a very careful job of graphing things, you should get something very close to Planck's constant. This assignment is due on Tuesday after the long weekend. So since you have nothing going on Friday and nothing going on Monday, I would spend some time Thursday working on this and seeing if you can get it done and out of the way. If you don't, then you're going to have some work to do on the long weekend, and maybe that's what you want. Something to keep yourself a little busy on the weekend. I don't know. You have to make a decision. Anyway, it's due next Tuesday. I hope that helps. We'll talk to you guys later. Take care.